Hi, I'm Doug, and welcome to Techniques for Watching Paint Dry. To begin with, the most important thing when watching paint dry is...
Psych! I'm still Kurt, this is still ComSci in 5, and welcome back. Let's get this garbage out of here. At this point in the course, we're going to take a break from looking at data structures in a linear way and start focusing on the math that backs a lot of the program analysis that you will be using in the future if you're going to ever write good programs. So what we're going to learn today is mathematical induction, which is just really an essential proof technique that you need to know if you're going to ever be good at writing efficient comp-sci programs and solving problems in an efficient manner. So if you've never heard of mathematical induction before, it's actually not very complicated if you think about it from the right perspective. Essentially, there is some statement that needs to be proven, and you assume that it's true, and you abstract away from the statement and replace the variables that they give you with other ones, and then you prove it that it's good for the next term, and in essence that proves the entire statement for all cases. For those of you who are visual learners, I have a ladder here. Mathematical induction can be thought of as climbing a ladder where the base case is getting on the first rung of this ladder, and then the inductive step is taking the next step or the next rung on the ladder. And if you do that in the general sense, you've proven how to get from here to here, then you can prove how to get from here to here, here to here, and eventually you climb and climb and climb the ladder all the way up to the top until you prove the statement. So our algorithm will start with a statement. We'll give you a base case, which is getting on this first rung of the ladder, right? We're going to assume that the statement they give you is true. We're going to write what we want to show. Then we're going to write out the terms, do the inductive step, which is climbing this rung of the ladder, and then we'll do a little algebra to make the conclusion, and the conclusion is you were able to get to the top of the ladder and prove the statement. Excellent. So let's dive right into it. To walk you through the math that we just did and relate it to the algorithm that we came up with to solve a mathematical induction problem in a general case, we'll go through it right now together. So we start out with a statement, which is the summation that they gave us. Next is the base case, remember, that's getting on the first rung of the ladder. And things to note that are important, we start at the beginning of this summation. It's very important that you start at the first rung of the ladder, not the second or the third. So for n equals 1, so for every time you see an n, you plug it in a 1. So we have a summation starting from I equals 1 to 1 of I don't know, is it equal to, remember, plug in the 1 every time you see the n, 1 plus 1 over 2. We find out that it is indeed equal, 1 equals 1. Great. Next, on our algorithm, we need to assume what they gave us is true. And what you say is for all n equal to k, remember, abstract away, change out your variables, assume that this summation holds. Remember, the summation is exactly the same as the statement, except the n's are replaced with k's. After that, we say, what do we want to show? to do that, we say we want to show the next step is true on the ladder, which is the k plus 1. So we want to say that that summation is equal to this, and every time you see a k plus 1, so you have k plus 1, you want to substitute in every time you see a k in what you've assumed to be true. So we have k plus 1, and for this k we have k plus 1, and then k plus 1 is k plus 2. Now we're on that step. Great. Now we know that we want to show this. Great. So now we do the terms. So we write out the summation. Note that this summation from I to k plus 1 of I is equal to the summation up to k plus the next term, which is k plus 1, right here. Now we use induction. By the induction of hypothesis, some would say, we can substitute out what we've assumed to be true or equal, which is here. We say that this is true. Therefore, if they're equal, we can take this expression and plug it into where this summation is. Now we're here and we need to go and show our algebra to show what we want to show. Through the algebra, we see, after we get a common denominator and do some factoring, that it is indeed the same expression. Therefore, we've shown what we wanted to show. We've gotten on the base step, we've taken the inductive step. So our conclusion is that the statement, remember now, what did you want to prove is in terms of n, don't forget to say that. In conclusion, the statement I equals 1 to n of I is equal to n plus 1 over 2 holds. Thank you for joining us today, and next on our subject to-do list is recurrence relations. What are they? Leave it to you to think about.